Action.
Action. All right, guys, welcome back. Today we're going to talk about the parent graphs, the graphs of the parent functions for sine and cosine. Now, it's a little bit different than just looking at the unit circle. When we looked at the unit circle, the sine was the y-coordinate and cosine was the x-coordinate. But now we're going to display that concept as a function where you can plug in inputs and you get out an output. You all did the task in your advanced algebra class of unwrapping the unit circle to produce the sine and cosine graphs, and that's essentially what we're going to do.
Hi, Mom.
So if I've got the unit circle, when we think about functions, we usually think about x being the input and y being the output. But on the unit circle, x and y are sine and cosine. Your x on the unit circle, the x-coordinate, is the cosine. So the input for our function is not going to be x. It's going to be the angle that produces that ordered pair. Okay?
I'm going to put an X right here.
Could you make that a theta?
Okay, Mr. Simmons, I will make it a theta.
Thank you.
I love that.
All right. Now, so our angles on the unit circle, we start at 0 and we go to 2 pi. So I'm just going to leave that blank because everyone knows the origin is 0. So I've got a 2 pi. I thought we calibrated these. I've got a 2 pi over there. Halfway between, I've got my 180 degrees, or pi. Between these two, I've got a half pi, or pi over 2. Of course, here I've got 1.5 pi's, or 3 pi over 2. So I'm going to look at the sine, where y is the sine of theta. Theta is my input, y will be my output.
Can I put Y here?
Go ahead, absolutely.
Why?
Why not?
Why not?
Okay, now if you think about 0 degrees, your y-coordinate is 0. Use a different color.
Because sine is Y and Y is 0. Orange didn't show up too good, Mr. Simmons.
All right, let's try something else. Oh, I'll use red. Let's make a big dot to distinguish it from the axes.
Okay.
Okay? At pi over 2, my y-coordinate is at its max value. It's at 1, so let me put a 1 here and a -1 here. At my next quadrantal angle, I'm at pi degrees, and my y-coordinate is 0.
So we'll put a red dot at 0.
And at 3 pi over 2, my y is at its minimum. It's at -1.
Which is about right there.
And when I come back around, I'm right back where I started with the y of 0, but my input isn't 0 degrees or 0 radians. I'm now at 2 pi radians.
That's exactly right.
And if you graph all of these little points around here, what you'll find is your sine curve of something like that.
Beautiful.
Hopefully, you'd actually touch bam.
Nice.
I keep stepping on the camera. You actually, you'll touch your points.
All right.
Now this is, when we had coterminal angles, any angle has an infinite number of coterminal angles because you can keep adding 360, add another 360, add another 360, or subtract. So the sine curve, really, it just goes on forever in both directions.
And that's pretty interesting because on the unit circle, we at 0 pi and 2 pi and 4 pi and 6 pi and 8 pi, all of these multiples of 2 pi's were all at the same place. They were at the positive x-axis. But now, if you'll notice, there's 0 pi, and 2 pi is way over here. Hello, right here. And then, of course, 4 pi is even further to the right. So now, I got a question, Mr. Simmons.
All right.
If this is 0 and pi over 2 and pi and 3 pi over 2 and 2 pi, what is to the left of the y-axis on the x-axis?
Well, my angles I start at 0, my angles keep getting bigger and bigger and bigger and bigger. In the coordinate plane that you're used to, you start at 0, you have positive numbers to the right, and you have negative numbers to the left. In terms of the angles, the negative numbers are generated by going around the circle clockwise. So here,
So, get you.
it would be a reflection of these points.
Didn't change. The student changed. Why is it not changing? We're good. We're good.
Except my values are all negative.
Cool.
In my graph, I'm just going to
That's
I did that
beautiful.
terribly.
I tell you what. Redo that, Mr. Simmons.
That was horrible. All right, I'll just start it from there.
These are not as easy
It's a
to
little
draw
bit
as
better.
you think. Most
You'll-
of you guys know this.
You'll get more and more practice with it.
All right, so remember when our sine, looking at sine value, when our theta is negative pi over 2, the sine of negative pi over 2 is negative 1. Remember the ordered pair at negative pi over 2, which is the same thing as 3 pi over 2, if you were to sweep clockwise, counterclockwise, is negative 1. The sine value, which is the y value when theta is negative pi, is going to be 0. The sine at negative 3 pi over 2, which is originally the positive y-axis or pi over 2, is going to be positive 1. Remember 0, 1, sine is y, y is 1. And at negative 2 pi, we're back to the positive x-axis where the order pair is 1, 0 and y is 0, so we're back to 0. So the ordered pairs where sine is pertaining to the function, the sine. All sine values or y values are going to be just like they were on the unit circle. So that's how we get this continuous sine wave or sine function wave with sine x. So let's talk about cosine.
Okay, let's
do that. I'm going to let you turn it. It won't let me turn the page. Alright guys, so if you remember y equals cosine x, I'm going to use purple I guess. Y equals cosine, let's use theta. X is another thing we could use, but we really want you guys to know that the independent variable value or input is an angle measure, not any old number that you can choose, any real number. We really want to look at it as being an angle measure. So now if you remember, if this is 0 pi, if you want to go 0 pi, usually we don't put that, but I will for emphasis. All the way over to the right is 2 pi. Now watch how we build this because you're going to be building your own. And then right in the middle is pi. Halfway between 0 pi and pi we said was pi over 2. Half a pi, very good. And halfway in between pi and 2 pi over 2 is 1.5 pi, which we call 3 pi over 2. So 0 pi over 2 pi, 3 pi over 2, 2 pi. Now let's put us some values up here. Again, 1 and negative 1. And you may recall that the value can't be greater than 1. Well, why can't the value of sine be greater than 1?
Well, the radius of a unit circle is 1. So the farthest right it goes is 1 away, which would be 0, 1. And the farthest left it goes
1, 0.
I told you I'm running on fumes.
Yeah.
Is negative 1. So that radius of 1 prevents it from going any further right than 1 or further left than negative 1.
That's right. So those are our max values. We don't get any larger than that unless we do transformations.
Right.
Stay tuned for video 2. Alright, so remember at cosine is the x coordinate, right?
Correct.
So the x value at 0 pi is
1.
1. So I'm going to change colors here. I'm going to use black. and I'm going to put a black dot at 1. In other words, we're starting at the 1 value, the max value. All right, so at pi over 2 cosine x, x is 0. So I'm going to put a dot here. Isn't it cool how we can write it at the same time? And then at pi, if we remember, cosine again is x. X is -1.
-1.
So we got to go all the way down here and put us a dot at -1. At 3 pi over 2, cosine being x, x is 0. So we're back to the x-axis here. And then at 2 pi, cosine is 1. And we've already established that, so we go up and we'll put us a dot at about 1. So what will this look like? I'm gonna try to draw this as best as I can, guys.
Nicely done.
Pretty good. All right. So the difference, if you'll notice, between sine x, you go and turn the page. Sine x starts at 0, peaks out at 1, goes back to 0, then it does a negative peak at -1. And or a bottom peak of min, if you will, and then comes back to 0, where cosine starts at 1, comes through the x-axis, bottoms out at -1, back to the x-axis at 3 pi, and then ends in a max value of +1 at the 2 pi angle measure. Alright? So, and just like sine, we can go backwards. Let's see if I can get a decent wave here. We can go backwards just like we could with 2 pi. I know that's not beautiful, guys, but you see what we do. The reason that this wave continues is that, just like he said, we have coterminal angles. We can continue wrapping around and around that unit circle. So what we end up with then is what we call a periodic function. Periodic in that it continues over and over and over, producing the same shape wave that we started with. So with these parent graphs, you should be able to draw 2 periods, if you will, from -2 pi to a +2 pi. You should be able to handle this. You should be able to label your axes with the correct x values and the correct y values up to 1 and down to -1. You've got to be able to do that because that's coming your way. Now, let's talk about a little vocabulary, if you will. All right? You're going to have to turn the page. All right? So, vocabulary. We said sine looks like this, where it starts at 0, peak, 0, negative peak, and then back to 0 on the x-axis. Now, Mr. Simmons, this kind of looks like the wave of an ocean.
Yeah, it sort of does.
And if we were to say that this would be sea level, if you will, then a wave has a height. And when we all see that on
a crest.
Yeah, a crest. That's right. We all see that on the TV. If you watch the news, it'll say something like, seas running 3 to 6 feet today.
Right.
That's this height right here above the sea level. What do we call this height, Mr. Simmons, that takes us from the middle of the wave up to the maximum value?
Well, in terms of, I don't know much about oceanography, but in terms of our trig function, we call that the amplitude.
The amplitude, A-M-P-L-I-T-U-D.
No, it's not from the peak to the valley. It's from halfway between to the peak, from the sea level to the top.
Well, while we're talking about it, what do we call this halfway point, this sea level point? What do we call this halfway point right here?
We call that the midline.
So mid-line, M-I-D-L-I-N-E.
It's a line and it's in the middle.
Straightforward.
Hey.
All right. What about the wave? I mean, we talked about the height. What about the length of this wave? Say from the start over here all the way to the end. What do we call one of those things? The length of a wave?
We call that the period.
Period. And it's not the end of a sentence where you use, what's the word I'm looking for?
Punctuation mark?
Punctuation mark. All right. This length is called the period. That's a terrible period. But anyway, it's called the period. It's the length of one wave.
Right.
We said it goes on forever. We're looking at 1.
And even though you start at 0, go up and come down to 0, that is just half of the period. You've got to go all the way down and back up again.
That's right, all the way around that unit circle.
Exactly. All the
All
way
right.
around the circle.
So there's 4 things that we need to talk about. One of them is amplitude, the height of the wave above the midline. That's vocabulary, write it down. Then there's the midline, the middle of the wave, vocabulary,
Right.
write it down. Then there's the length of one wave,
Right.
the period,
Period.
write it down, vocabulary. There's one other thing we need to talk about.
Really?
What do we talk about when we talk about the position of this wave, if you will, within the coordinate plane? Left and right position. What is that called? Starts with a P.
I was going to guess horizontal shift, but that doesn't begin with a P.
No.
Maybe
Called the phase.
phase shift.
Phase,
I thought
that's
there was
right.
an H in there somewhere.
That's right. The phase shift. Now sometimes we don't have a phase shift, and that phase is identical to what it normally would be. We call that the parent graph. But if we move this wave left or right, and in video 2 we'll be talking about transformations, we get what we call a phase shift. So in normal position there is no phase shift. I'm going to write this right here. Phase, P-H-A-S-E, shift. Make sure there's an F in there, or you might write something inappropriate. So there's 4 vocabulary words you guys need to know in pertaining to parent graphs.
The parent graph does not necessarily have a phase shift.
No, it has no
Right.
phase shift. It's only when we transform it, and we'll talk about that in part 2. Rammed it on.
That is an example of a phase shift.
Exactly.
Let's move it back.
Okay, so if we want to change the amplitude, then we can grab this and stretch it up.
Can I grab
And
this one at the same
yeah.
time? Okay, that's much
Sure.
better. No,
It's not wanting you to grab it, is it? No,
No,
just
grab
me.
it.
Anyway, if we stretch the wave like this, obviously it's going to affect our amplitude.
And I really like how the amplitude stretched with the graph.
I did not want
Yeah.
to do that. That's pretty cool. All right, so we're going to put this back to position the best we know how. All right.
Okay.
Now, so there's one other thing we can do. We can stretch this period. We can change the length of a period. We'll talk about what it is in video 2. But if we grab this wave, there we go. Then we can stretch this wave out. Now notice how I'm stretching it out this way. So now that constitutes a phase shift and a period change.
Right.
So we'll be talking about that again in video 2.
But if you stretch out, I can't do it. If you stretch out the graph and it still goes through the origin, it's at the same starting point, it's only a period change.
That's right.
It's shifting this point left and right that makes it a phase shift as well.
All right, just a quick little recap, guys, and we're going to let y'all. You have to change it for me, Mr. David.
Go back.
Yeah, all the way to sine. Y equals sine theta or sine x. We're going to probably stay with sine theta. Theta is what we want to use. Looks like this. Next video, next slide. Y equals cosine theta, and then of course there's our vocabulary. Stay tuned. Video 2 is coming your way. And
Nice.
cut.